All right. So you start with this in ANSYS. You start with this package called Workbench. Initially, you want to go to this link. If you don't have ANSYS, go to this link here. They'll give you to the ANSYS for students. So it's a free student version of ANSYS that you can use. It's actually free forever, but the license, whenever you download, so you give you 1 year license. But next year you have to just download again, and you will usually to be a newer version. But basically you can keep using that for as long as you want. But again, study purpose only. So it's free, and it is also available in your computer labs. If you walk into any of the computer labs in our school, you should have ANSYS pre-installed. But there's one thing you want to remember is if you want to, for example, your group want to use your home computer, also the lab computer, you maybe want to match the version. When you download, you can go and get the prior older versions. So, for example, you want to match your lab computer version. Otherwise, you'll have trouble you can convert it to newer version, but you cannot convert down, and you will have trouble sharing files between lab computer and your home computer. Okay, when you download and install, you will get into this workbench here. So you can see here, the workbench is like an integrated point of all the functions of ANSYS. So you see most of the functions. You see something you're familiar with, like transient, like structural, static structural, like fluid dynamics. All these sort of things are all in one place, and you can model different things in one file and link them together, which is very useful. In our case, we want to start with this model analysis, which gives you natural frequencies and mode shapes. Okay, so all you need to do is just drag it into your workplace, and one of the things you can do is you can share some existing information between your model. So you just need to drag those lines. For example, you want the previous model, you want the same geometry, you can just drag that in. That's very easy and straightforward. But I'm going to show you from the beginning, so just forget about that. Just look at that. So as I mentioned, the first step is to define your material. Okay. So the material is under this engineering data. If you double click, you get into a material list. So in your so by default, we're using structural steel. So if you don't change anything, the model will be in structural steel. But in our case, it's aluminum alloy. So we want to add aluminum to your material selection. So there's under this engineering data source, there is a list of common materials. In general material, there are other materials. In general material, there is aluminum alloy. Okay, you just simply add. Then the material is added in your set, in your selection set. Okay, so that's done. Obviously, you can, if you want to, you can change the values. For example, Young's modulus by density by default is 7,850. You want us, for example, you're using a special aluminum, it's 7,900, and you can just change that. Okay, you can change those values, but we just use default for now. Then the second step is to define the geometry. Then you can import the geometry into your system. So I'll just right click and go into splice plane. Okay. So there's different ways, different package options that you have. So you go into splice plan, and all you need to do is draw a line. So because we need to pin at a point, so it's better to draw in 2 segments. All right. So we just need to, like I said, all we need is just draw some lines. Okay. So I know my pin point is about 250 millimeters. And the next one is about 375. And done. That's a geometry. As I mentioned, this is a 1D model, so you just have one line here. I'll have to define the cross-section or profiles. Okay, so just add a new profile. So there are options: square or rectangle beams, T-beams, I-beams, or other shape of beams. But we're looking at rectangle beams in this case. And remember, there is a hollow rectangle and solid rectangle. So we are solid rectangles. So now we added the beam profile, then we just need to edit. So we know in our case our width is about 18 millimeters. Sorry, not here. Sorry. This one. So it's here. So this width is about 18, and on my thickness is about 3 millimeters. Okay, so that's our cross section. So it's done. Close it. Now I have to assign my cross section to this to my geometry. So all you need to do is prepare. Where is it? Oh yeah. So now we select our rectangle beams. You can give it a name if you want to, and create a beam. So all you need to is just click this one, click this one. Okay. So now they become beams. They're no longer. All right. Then we go back to the beams. See, now we have 2 beam objects. But now the 2 beam objects are independent, so they just by their own. So you need to join them together. To do that, you just need to create a part. What happened? Why can't? Okay, so I just need to select both of them and move to one component. So now we have a new component, then that inside that component I have 2 beams. Remember, you have to say inside this component I want to share the topology. That just means all the members are joined together. That's done. That's our geometry. Okay. Let's close that. Then we go into the model. Inside the model, we need to define our boundary conditions. So we need to define our boundary conditions, and also we need to define our mesh. In our case, mesh is not that important because this is such a simple geometry. But just in general, if you're doing an FEA, mesh is probably one of the most important things to deal with, because generally, the finer the mesh you have, the better accuracy you're going to have, and as well as a longer computational time you're going to have to deal with. So you have to find an optimum mesh or a good enough mesh to give you good enough accuracy and reasonable calculation time. But in our case, we don't need to worry about that. So mesh, just generate, update, or generate. So just give you a standard mesh. So you see, it gives you about roughly 10 points in each section, which is again good enough in our case. If you want to see your 3D shape, you can show the 3D shape. So you can show it's 3D, looks like that, and these boxes is your mesh. Okay. All right. Okay. So now we need to define the boundary conditions, right? So firstly, we want to fix the end. So the fixed end should be here. Yeah, the fixed end should be here. So just under model, environment, and fixed. So we just need to select the point here and say apply. So that we fix this end. Again, we want to show the section. And we want to pin at this point here. Okay? So another way to call pin is called simply supported. So that's the same meaning of pin. So basically, in physics, it means it constrains all the translational displacement, but allow all the rotations. Okay, so that's called simply supported. And we want to simply support it in here and apply. Done. So now we define our boundary conditions. The next step is to define what sort of result, what sort of output you want. In general, did I click something? In general, we want the deformation. So in this case, the deformation is the mold shape. Okay? You want to define how many modes do you want to solve for. But it's critical to understand the software doesn't know whether this mode is a transverse mode or is a torsional mode or is an axial mode. So they will just give you all the modes lumped in one big table. Okay? So you might want to have more than what you think you want to. For example, we probably put 20 here. Later on, you'll show what are those 20 modes. Okay? So then we just solve it. Sorry. There's one more thing, because we define the material, right? So initially we define the material as by default the material is structural steel. So I just need to set this as aluminum and run it again. Yeah, as I mentioned, being a 1D model is very efficient, so it takes almost no time to solve. And boom, we have our results. So the first one, you can see this is a big table of all the natural frequencies that I mentioned. It's in Hertz, and the first one is our first mode, right? So remember what was our experiment results? It's about 13 point something, 13.1, about 13.1. But our analytical solution gives us about 13.4. Okay? So anyone think about why we're getting a bit higher number than what we experimentally measured? Some possible reasons? Yes, why is that? Well, I mean, yeah.
Like just where you've got support and maybe the fixed end is exactly different.
Yeah, exactly. So when you have a fixed end, in FEA we have an ideal fixed end, but in reality we usually cannot achieve that. So even if you have a clamp and very, very firm, you will still have stiffness at that point. And when you have some sort of stiffness, especially when you deal with a vibration of metal, then that can have this type of 5 or 10% sort of difference. So that's one of the reasons. There could be other reasons, like the pinpoint that might not be very rigidly pinned. It could be some damping inside that. It could have also the stiffness inside of pin end. But there's an animation that you can play, so that's how the vibration can be done. Remember, if I turn this on, you probably have similar. Hopefully we'll have similar motion of the vibration. Although this is much faster. And this is not in real time. But we have a null point here. Okay? Alright. So remember we have this big table. How about the second one? Is this one the second mode of the transverse vibration of that? Anyone guess? Good.
Is this what the second value that you get?
Yeah, this second value you see in that table, which is 80.5. Or can it be something else? Let's see. So to show the second, you just need to right click and say retrieve these results. Oh, it's not. It's not because it's in this direction. Okay? So it's actually a horizontal transverse vibration. Okay? So actually the third one in this list is what we want for vertical vibration. Okay? So you get the point. The software package doesn't know what type of vibration this is. So they just put everything into one big table and give it to you. So you have to, like what we are doing, just look at each mode shape to identify, okay, this is the third mode of our vertical vibration. So you have to look into each of the modes to identify what type of vibration these are. So this is very important. You can't just say, oh, this is a sixth mode, but in fact, this is a torsional mode. Okay? This is actually the first torsional mode of the system. See this? Okay? So that's also in your assignment. So you have to find torsional mode. So you have to look into your solution to identify which one is your torsional mode. And obviously you need to plot the mode shapes like this. You see this mode shape doesn't look right. We have a lot of area being blue. And only, the shape looks right, but the contour, the color doesn't look right. And also you see those numbers are extremely small, right? So I made a note here. This is something, where is that? This is a little trick here. So to show properly the mode shape of torsional vibration, you need to insert a user-defined results in the solution section. Then type Rx in the expression options. So this is a very special thing that you need to do. So you want to insert a user-defined result, and in the expressions you want to type in Rx and enter. Then you just solve for it again, and in that one we want to retrieve the 6 modes. So now you have some meaningful numbers, and more importantly, you have the right control. Okay, so now you see we're getting equally spaced contours, which means which is the mode shape should be. Yes. So the Rx, it will look more realistic if it's a cylindrical vibration. But if you learn about mode shapes, the amplitude of mode shape doesn't have physical meaning. So it just look at the shape. Okay. So it can be this might be exaggerated, but it should be in the radians. Well, it's not in radians, but it's proportional to radians. Yeah. Okay. So where we are. So now we have this one. We just want to double check. Okay. So remember our third mode here. It's actually the second mode of that, and we have about 90 hertz. All right. So let's have a look whether we can apply that. So all we need to do is to change my forcing frequency to around 90. To show this is probably the best we can get. Feel free to come closer if you want to. So you can't really see much, but you can see a bit blurry in here. If you look at this spot, it's a bit blurry, right? And another thing to show is this is something metal that you can see. If you look here, you've got this jumping from this one. But if you put at the low point, which is right here, you can nicely rest on it without making too much noise. And obviously so this agrees with what we see from here as well on RX. Okay, so if you play the animation, you sort of see we got a lock point around here, and we can see that the lock point around here. Roughly, okay? And to see the frequency, all I can do is just look at the dial here, to be about 90, maybe less than 90. Alright, so that's pretty much what we want to cover today.